thank you very much for inviting me here to your seminar. Our work on evolutionary computation for change constraint optimization problem. Yeah, I'm a researcher at Optimization Logistic Group at the University of Adelaide in Australia. So I just short to my bio. So I'm a computer scientist. I have done my master diploma 5 years in Germany in Technical University in Dortmund and in Kiel. And I made my PhD in Adelaide. Since then, I am working in Adelaide in the School of Computer Science, and also I was a researcher at Integrated Mining Industry Research Consortium for 4 years, and I'm now leader of a real-world application group in our school. So this year, I would like to invite you, it's still time to join our workshop on AI-based optimization in Melbourne for 4th, 5th year in August, where we usually meet every year and just connect with another researchers in Australia. It's really lovely. So also I'm finalist of Fulbright scholarship in South Australia, and was invited as keynote speaker to a conference where I have this could present our work on mind planning and the uncertainty from theory to practice. Also, we have several best paper nominations for our work, mainly in our prime conference, which is Genetic and Evolutionary Computation Conference. And
Gecko,
yeah, we have always the gecko. So this year it's in Malaga, so it will be also hot. And yeah, so we have like different tracks there, and yeah, we were really happy to get Best Paper nomination and Best Paper award last year on several work on evolutionary optimization, like especially on quality diversity approaches.
the 3 times of nomination.
Yeah.
Finally got it.
Yeah.
That's amazing.
Yeah, it's pretty much, it's working pretty much, so you can vote, and it's a lot about your presentation, how the students got the presentation. It's like, yeah, we got it last year, and yeah, and we this year also are nominated, so you please vote for our paper. Yeah, and I also am very fortunately to have done several like visiting research studies in Sorbonne University, also in Leiden, Nottingham, and of course in Germany. So it's very nice collaborations. And my talk today, it's about, I would like to show you how evolutionary computation methods, and especially multi-objective evolutionary methods, can be applied to real-world problems, optimization problems, and especially focusing on uncertainty, so in which this can affect the quality of the solutions. So it's not just like optimizing here. So for example, we can you can imagine we can evaluate the performance of machine. They are not given exactly the same results each time, because if the parameter are changing. Also, you can imagine some example if we travel like from one city to another. So this plan load also can be different, and we have different uncertainty. It is like on land, on in the air, how we really see the world is very unsecure. So here's like short introduction. The noise can occur in different stages of the optimization. So we see here a theoretical study. We can distinguish noise when it's applied before and after a function evaluation. So in this case, we call this priori noise. We affect this, where we see the effect of solution before the evaluation, and here the solution component may change before evaluation, and posteriori noise, where we add some noise to this function, which we optimize, and this will be depend also on our maybe unknown or no distribution. So here we know there are many difficulties arise in this stochastic optimization, as this realization is unknown, and we want to have some knowledge, ground knowledge. Often it's gathered while we implementing the solution, and we see the problem in real time. So this knowledge can potentially be used to reduce uncertainties in this sense. For some components, they are not implemented. So we can just like include this new knowledge. And we also can cover selected sets. Here we will cover a selected set of the topic for stochastic optimization using evolutionary algorithm. And I was wondering who from you are working on or hear about something about evolution?
Almost nobody. We know some basics, but
Yeah, I think because my previous work, maybe I have one work maybe 5 years ago.
oh yeah.
I use the evolutionary algorithm for tensor networks, maybe schema design new of this. Yes.
Yes.
This is why, yes, I think the top topic you introduced is relatively interesting. And I'm also very interested, like in the recent past years, maybe fewer and fewer people focusing on the evolutionary algorithm again.
Yes,
Yeah.
yes, exactly. And now it's like I see like on AI conferences arising this hybrid methods here. You can use ML methods with some evolutionary algorithms. But also like for industry, if we talk with some industry partner, there's a lot. They just because they have to have certainty and use optimization using evolutionary algorithm, and they won't have this multi-objective kind of threshold here. So here, just like very shortly, because we know it's like what I would like to give you some insight. It's there are general purpose algorithm, and we call this like follow this Darwin principle of survival of the fittest. It is like some parallel. This means we work with a set of solutions that we call population. Then we have at first stage this parent population that produce offspring population. And this can happen by different operators like mutation operators, crossover operators. They can be also used especially for developed for especially for this problem. And then next step, we select individual of this parents and children solutions, and we create new beta population using this fitness evaluation. And it's like iterative project process where we look at when we can get this good solution, what it's mean for us. So overall, evolutionary algorithms are adaptive and often yield good solution for complex and dynamic and also on stochastic problem where just like exact method can like MIPS solver can go find in this time any solutions. This is an outline for the presentation. So we had like introduction. Now I would like to show you our example of our work, where we work like on theoretical insights, and also we apply this to mine planning under uncertainty with industry partner. And next part will be submodel optimization problem with change constraints, and go to the conclusion. So this is the real world application. It's in somehow amazing. This is Australia, exactly. So we know this like this importance of this uncertainty. It's fascinating to understand and also predict, but also mitigate the uncertainty in these processes. And this is uncertainty also was applied in a lot of engineering problem, physics or finance. So, and here now, taking into consideration the increasing population, and there are some prognostics, especially in Asia, yeah, and they show us the need of more critical minerals for renewable energy from electrical car and so on. So it's growing problem, and why we need this critical elements, because they are around us everywhere. So we have like this in computer, mobile phones, and wind and solar power energy, in biomass fabric, electrical vehicle, and diverse sensors and medical instruments. And how it's this demand looks over the years. I hope, yeah, you can see this plan. So we have on one hand, we have increasing metal demand and increasing global population. And another hand, we have, unfortunately, decreasing ore grades. What you can see here on this plot, this yellow line, it is our gold grade, and blue and red, it's like copper grade. So you can see like 150 years ago, we have really a high percentage what we can find here on minerals, and it's like the general trends for actually lead, zinc, and all minerals going down. So now we are pretty much looking in Australia, and the mines about like 2 grams per ton. So it is like 10 times less. And also we have here prediction that all actually minerals and metals, except lead, will grow. Here how you can see this prediction, even 500, 300 copper and zinc and iron 100%. So demand it's enormous. This is good for Australia. Okay. This is like showcase you the importance of this problem, and here it's like a kind of characterization how we actually get from this debt, yeah, and to this concentration metal. So there are different stages in the mine problem, and we are concentrating in this important mine planning and development. So actually we want to know what is worth this ore material on the end of the day. So here you can see some software program would show you how the blocks in this mine will be scheduled. So we looking on optimize this revenue, taking into account each block and model this, and this capture for us this maximum economical potential of this mineral resources. So the long vision is we want to optimize this long-term plan. It's like often like over 20 and sometimes 50 years. Based on this geological estimation, what I would like to talk shortly to order to develop mine scheduling process. And actually, what is this uncertainty now have to do with our model? So you can see how actually it's working. So first we have like some exploration on boreholes. We get like in computer great boreholes from this. It's very costly. It's pretty much like $500,000 per one bore, and few meters in labo to look at on the concentration. So we go through different stages like modeling, and then we establish here main block. We have just all these blocks, and on the end this graded block of this ore. And these are the samples from this boreholing. And how we now deal with these uncertainties. So what is interesting in our case, so you can imagine we have this block model, and this will be like 1 meter by 1 meter. And this was like a collection of specially located blocks, and each block have own attributes. Yeah, they have like rock lithological domain, ore grade, rock density. And you can see we can establish, based on this data and like several hundred runs of neuronal network, some prediction. But what we can see of this prediction, for example, percentage of copper, it's will be for this block 0.4, 0.2. So those are very, very different predictions. So, but we still take this insight. And you can see, and on this insight, we can look it in such a body and establish now it's like for gold, and establish where is the highest concentration of the gold based on our prediction. And we can get like 100, 200 and more such a prediction for this space. And we can see there's a lot of uncertainty, which are actually most predictable. And here we come with our like computer science approach to the engineering problem, where we have established here a random profit, because each block will have profit based on this economical evaluations. And we use this, we use not only one block, we use many blocks together and call this parcel of these materials. So we will get here some space between 0 and 1 when where we want to have here, our goal is here, we want to compute solutions for profit, which we can guarantee that as profit, it's at least P with the probability at least alpha. So have some confidence to this. And we aim to maximize our profit, because everything will be all about, netto present value for this. So we use this change constraints characterization in this way. So we establish here, we have expected profit, mu, and sigma is our variance of each parcel. So we have here expected profit and also the variances of this profit of solution. Now we have to make assumption to use this formula that we have independent and chosen according to normal distribution, and based on our previous paper on limiting the effects of uncertainty for knapsack problems with stochastic profits, we establish here our fitness, objective fitness, where we can optimize, and this is our expected profit. Minus some parameters, so it's based on our variance, and some f of alpha, which is L fractional point of the standard normal distribution. So that's mean if we increase this parameter, we will get our more conservative schedule for the mine. So there are like another theoretical motivation on this, because we want to also to take it into account our covariance between our parcels. So on the end, we will have, and I will show you shortly, we will have some mines. Then we correlate these parcels and try to mix this in order to minimize the uncertainty based on this. So we establish here, based on this covariance calculation, we establish another fitness objective function based on Chebyshev equation, and we calculate this in our process. So again, we followed our approach, where we want to have some guarantee on our profits. And we will see our alpha will be chosen, like, for example, with 60% or 90 or 99%. So this is our key objective function, and and this was like new approach to determine this schedule and the uncertainty, which provide this probabilistic bonds. And in this sense, it's so important because we are able to guarantee these profits based on this uncertainty, which is measured here in the terms of the variance. And now I'd just like to show to an experimental setting. So first we have like two models. One is just to give you dimension of the problem, we establish together with experts, mining experts, some test model where we have like 18,000 waste blocks and 8,000 ore blocks. And we have here this alpha values, this parameter set to 60, 90, 99, and we have discount rate for this company 8%. And we also, we will see like we run this on 10 assemble members. And another example, we have real data, which is like complex model, new established in West Australia and based on 200 blocks. Also the data is anonymized and free available. So what is in this domain very great. And here you can see, you can imagine now what we can do. We have two east and west blocks, and this red, they are all waste. So first we have to dig this waste up, and then we have two area with different percentage of copper. So one is like higher copper and one is less copper, and it's like what our schedule will do, how we progress. And the first plot, I think it's such interesting problem. You can see we have like 6 periods. This is like 6 years, and here in this X we have netto present value. So we can see the standard strategy what is used professional how they establish this mine. And this on the right side is like our uncertainty discounted strategy with our new approach. And you can see this, not only we are able to through these years get higher NPV value, but based on this information of the uncertainty, but also if you look of these 10 assemblies, the variance also is less. So it's more robust and it's more useful for the company. So it's kind of this deal as like enhanced decision making for this discounting process in the mine planning. And we have some data on this, but only like would like to show you this is like this classical strategy, and we have different uncertainty discounted strategy, how far we include this uncertainty. So here it's like we have very high uncertainty on this domain, on this geological domain, and you can see you can look on this mean expected value for the profit. So this bold, there are higher number in these years, but also what is interesting to look on the standard deviation, because we won't also have less standard deviation on this. And even with the 60%, we have very good results. And also here you can see 90%, 99%, and we can see we have also in the middle higher value of in the mean, but also less variance. And I can show you, this is also very interesting, like overall example of this work. The first is this strategy. So it is like how I say, first is this left-right plate have higher copper percentage. So what the scheduler actually do, of course, they will totally dig only one pit, yeah, and then after this, then with the lower copper concentration, and you can see here 10 members over 10 years. How is here's we see the profit, how it's developed. So we have some kind of in period. This is 6 kind of less profit, and this is the new approach, and we can see how now the solution are chosen. So we can mix we can mix the uncertainty of this the correlation between the peaks, but also we can move this uncertainty in the later stages, what is also important. And you can see here we don't have any just kind of, it's more robust. We don't get kind of like down peak, and also we have less variance here. So this is like the main actually intended solution what the company come to us. And this is this real world example. And again, you can see the first plot. It is like how will be work until now. And now in the software, you can see you have the smooth go with NPV, and also the variance is less smaller. And this showing also, I think here, what is really absolutely important for the miner. It's not only to get like a better number, because NPV, of course, if we take into account the uncertainties, overall our NPV will be less, but we have also a lot of smaller variants. So you can see on this first years, we really really have less uncertainty. So do you have any question to this before we go to submodular?
Yeah, may I ask a question?
Yeah.
I'm not sure if I followed everything here, because I'm not very familiar with the education part. The question is, yes, you, so I want to confirm that you do not use the evolutionary algorithm to solve the optimization problem defined in your slides, which is to maximize the profit with constraint by some probability, right?
Yes, yes.
So my question is, why does Neumann is, for me, if like me to solve this problem, maybe it's an evolutionary algorithm, maybe not the first choice. I would consider the Bayesian inference or some other optimization methods. So my question is, I'm wondering why you choose the evolutionary algorithm as the tool you solve rather than other techniques.
Yes, because yes, this is a very good question, but the answer is also very simple, because we work in this mining consortium with the university and like over 20 companies in BP and so on. So they are using, actually the company are using in-house evolutionary algorithms. So all this strategy are evolutionary algorithms. And also another tools they are using, because we make some study like on this, also are developed on evolutionary algorithms. So yeah.
Have you ever seen any like a systematic comparison between like evolutionary algorithm and some Bayesian optimization kind of machine learning approaches?
Yeah.
We are more familiar with them.
Yes.
We believe machine learning methods are good.
Yes. I think this is very interesting. So we have like done study again like with multi-objectives. So when we take another objectives into account, and the point is, I think what the company, they are not using this version, maybe in this sense, I assume they're looking really too much at the time, and they have really time constraint, like they have big clouds, but they say, just like they have to run less time, they won't have something good, not the best, like in a few minutes, and they run again and again, all 24 hours, because they have new information from the blogs, and again. I think this, and they just pretty much stick to to this algorithm. But this, like from us for scientists, is really interesting how this your methods will perform on this real world application, But the time is also an issue.
Yes, it's very possible.
So I have one more question. Like you mentioned, maybe they prefer good than the best. Right? Like if my understanding is correct, that means they prefer low variance, then like low bias. Can I say that? Like sometimes they are willing to sacrifice some bias. Like for example, if you mine something bad, that's okay. But if it's risky, no, they are not prefer it.
Yes, exactly. Also, yeah, also like the companies and engineering at all, it's very like robust and classic. Yeah, it's very hard to go into with new models, and how to say it's not about the numbers. And here also it's like, oh, of course, exactly. This is like only a few millions. Yeah, they will even like 2, 3 numbers, millions, this is like okay, yeah, because this is what they get like per day, yeah. And they won't have like, for example, like even like why is this 2 bits? Because this Neumann, it's so big. I think they said it's like for over 50 years, like and it's just like, and they actually, because they are so big company, have so much machinery, so they will establish not only 1 bit, they will establish really 2 bits, and they want to do this and 3 even simultaneously. I'm like, okay, this is again even bigger problem, and also here I think it's the key. It's like they how to optimize this to make not optimized solution, because they don't want to have this extremely peak up and peak down, just like how here they want like just like this is really interesting how you talk with like managers. Yes, like we won't have this curve like smooth, and we won't have extremely be secure in this first few years, because there are some example in Australia also company really go bankrupt. Like 3 years, it's no profit, it costs. Banks, credits, 4 years, nothing, it's done. Yeah, I think the biggest example was with the forest. I don't know if you hear this mine magnate. They have like maybe 20 years ago, some company go bankrupt. Now have again another one. But it's like, yeah, so we have to consider more this uncertainty, and we can, yeah, have less NPV per day per year as more certainty. So they are pretty much very into it, because the company and they would like to include new methodology, ML, AI, everything, but it's like have to be very robust, really showcase them uncertainty first, because they are very conservative. Yeah. So taking the risk, because if they change something and it's not working, then it's really big. Yeah, just for them. So yeah, so it's very interesting how we just can just like develop from even like theoretical bounds for this chain of Chebyshev approaches, and take into company and see how this is working. So that this is like a real software what everyone can buy. It's tool for uncertainty, and they are doing like every minute, yeah, running this algorithm on this. And next part, the second part, I would like to concentrate on this multi-objective approaches, again evolutionary, for change constraint submodular problems, and the motivation. I think it's also interesting because the submodular problems are so big a group of problems. So probably you are also looking in your work. So here we have. And again, we can look at the problem involved the stochastic components and then constraints that can be evaluated with some small probability, for example, here. And again, it's just like we have here solutions, and now we have here given submodular problem for this. And it's like, for example, here will be the sum on random weights for this problem. We have B, which is our bound, and we have this change constraint in this form. So we want to look at how this constraint how this weight bound can be violated, but only with small probability. Yeah. So so this submodular function, so a function that model this problem of diminishing returns, and also allow to model many real-world optimization problem. And here we use evolutionary multi-objective algorithms with this Pareto optimization approaches, which are also show a good performance theoretical and empirical for this problem. And here again, I would like to ask you if you overall working of the submodular problems, looking into submodular problems, or you
Minimization, maximization.
yeah. I just I can show you like example of what is like submodular problem. If you problem are in this family, it is like this is simple problem on sensor placement. So if we have here a room and with like temperature, if you have like one sensor, then we will have the maximum coverage, for this. And we can place different sensors in this room, and it's like sensor placement problem. So submodality as per se, which different formulation, but this one you can imagine here you have you will add here one new sensor in this room, and you have your set of sensors B, and also you have sets of sensor A. And now what it's mean, if you now to this red solutions get new sensor, you will have from this equation marginal gain will be to adding this sensor is greater if you add this to the Z A to the smaller Z as B. So it's like you add more sensor, but you will have diminishing result, And example of that such a submodular function are, for example, linear function, cuts, coverage in different settings, also rank of Metroid. So it's everything will just include the submodular functions. And now the change constraint, again, we use this for this submodular function is because their difficulty lie on how we evaluate given solution that fulfill these change constraints. And we use here independent normal distribution, distributed random variable, which can be done exactly because we have formulation for this. But in other cases, we can also use sampling methods to evaluate the probability of validation. But also another way is to use this surrogate function as Chernoff bound and Chebyshev inequality to determine whether the solution is feasible or not for us. And these bounds don't allow a precise calculation for the probability of the constraint violation, but they give us upper bound and the solution is accepted if it's upper bound at most alpha. So again, we have a probability on this and not exact number, but we can also establish a condition based on this expected cost variance and constraints to show how the given solution can be feasible. And here in this work, we consider global simple evolutionary multi-objective optimizer. This is like a simple evolutionary optimizer with, you can imagine about this evolutionary process, we use also the axis, so you will have all solutions what we have but it's also multi-objective. We use here non-dominated sorting genetic algorithm. I don't know if you hear this algorithm. I think this is most, if you look at like by Google, like in the citation, this is like the most established multi-objective algorithms and very wide use also in industry. Yeah, this is like, this is ready to go, multi-objective optimizer. So we have another SPIA2 optimizer. And then now, based on this algorithm, we look at on the optimization for the stochastic constraint submodular function. So we use here B-objective formulation, and we show here theoretical performance and also state-of-the-art practical results for range of submodular problem. And here there are the settings. So we have two settings. One is random weights of a given set of items, and one is we assume that the weights of the items are chosen independently from each. So we have here ID weights, and here we have weights with the same dispersion. And you can imagine here on this plot how this will look. We have here, this is our constraint bound. This is one objective, and another is this function value, what we want to minimize or maximize. And because it's multi-objective, like B objective, we get Pareto front to our constraint bound. And this B objective approach use different multi-objective evolutionary algorithms. They are working very much in this greedy behavior, and we can use this local Z here, and we benefit between these trade-off solutions, yeah. And on theory, what we can see it's the same. We can show the algorithms have greedy behavior and allow obtains good approximation results. So we have theoretical the same approximation as greedy on this evolutionary algorithm. And in the practice, we also see then the algorithms lead to high performance. So now what is can change now is what it's novel about this approach is we use here this change constraints. So it's this bound, for example, can stop earlier, some probability, and then we want to look at how big is this gap, yeah. And what we calculate is the gap. It's not too big, so. So this is why we have also good results on the end, and we have here like different for different uniform IDD weights and with this uniform weights with the same dispersion, different theorems. This shows this simple global multi-objective optimization algorithm have good approximation, one of the small o, and also really good time evaluation analysis. So there are this lemma, what we just worked through based on this Chernov and Chebyshev. And again, now we can use this in our experiment, how when we here calculate expected weights, for example, function, and this will mean either on delta or variance and alpha. And I show you how this work nicely, and this is like, again, this is like the submodular function with these change constraints in stochastic setting. So we have to use this type of equation with WS is our sum of these random weights, our constraint bound, and now we establish here this fitness function. So one function, and I go not in details how we write this, but one function establish as tightness for the constraints, and another is measure our quality like of the solution in the terms of the given submodular function. Now one is like objective function, submodular vector function, and one we're looking on our constraints. So we want to optimize both. And to this main results is that's the global ZIMO using this multi-objective formulation based on this two tail inequalities achieve the same approximation guarantee as study greedy approaches. And we have done results on influence maximization. with uniform change constraints, and here you can see different bonds, alpha and delta values. And the first row is the greedy algorithm. Here's our simple global ZEMO. Here it's more advanced NSGR2 algorithm. So you can easily see on this mean values. So we have higher values, and especially if the bond is higher, so they perform better. And you can see this both algorithm statistically over 30 runs outperform greedy algorithms, and especially global ZEMO even outperform NSGR2. So what we are thinking, what is the explanation is for this NSGR2 is working with population of 20, and it's probably in this algorithm are not able with this population where we measure this crowding distance is like too far on the Pareto front, so we have like bigger gap on the Pareto front, and it's not performing well. And I think this is interesting because like usually everyone will use NSGR2, yeah. Just like, but it's for us interesting to how this work with this change constraints setting, and why is this happened. And this is another example. We use like another sophisticated SPR2 algorithms. We have like different objective function. So it's just like won't go in the details, but you can see overall. Yes, overall it's even SPR, it's better with this of the submodular function, and we can see this very nicely on the statistical tests. And here's interesting experiment to which indicate us there's the population size, because often in evolutionary computation it's question, yeah, how big we have to choose this population, 20, 10, maybe 100 solution would we work through the evaluations. And we can here show this the population size and the fitness value, if the fitness value decrease for all our this delta uncertainty values in both graphs, which mean larger population do not improve the performance for NSGR2 for the setting.
That's the next question. Why is it the number of the individuals of current size do not? Because in my understanding, the number of individual is very important in this algorithm.
Yes, but this is like a really yeah.
Yeah,
good. This actually good question is have to do with here how you calculate evaluation in through this algorithm, because you have to choose this if you have to count each evaluation. So it's different if you have like mu is 20, and it's different if your mu is 200. So you have to, in each step, if you use population 200, you have in one step you just move 200 evaluation. So it's mean if we this algorithm NSGR2 20 have more time, yeah?
yes.
Because they go faster through this 20 population.
Yes, I think.
Yeah,
Yes.
we have because we count evaluation.
Yes. Do mean that you assume the total number of evaluation is controlled, is upper bounded, right?
But yeah, you have here function value, and you are going because it's not like always if you just because of this evaluation number. So here, for example, even starting point is you get lower function value because it's because you carry out 200 populations. You have to calculate for each step to this. But sometimes this is like push this evolutionary computation, the steps, so that they try to evaluate automatically which parameter setting is good for the algorithm for this problem. This is like big question in this area. How you can see, because actually they will naturally we will say yes, with higher population it's will go faster to the better result. And this is like a short summary. So I hope like I could show you here these approaches are able to deal with this stochastic constraints in an efficient way. And I think I have a short short additionally topic on profit-based discount knapsack problem, which we also use to our work. And now we here consider classical knapsack problem, and now with stochastic profit, not weights as before. And we aim to maximize the profit value. When we guarantee, then we achieve a solution is with the probability at least 1 minus alpha of p. And this is like a definition of the stochastic knapsack problem, where now the profits are stochastic, but the weights are deterministic. And in the mining example, we have the weights, the block size was stochastic. And again, it's our goal to maximize the profit along our solution, where we can guarantee there's only small probability this alpha of p will drop below our p, where we maximize p. And we use another more classical algorithm. It's 1+1. Also 1+1 with like special heavy tail mutation and μ+1. And discounted greedy uniform crossover. So we are very specifically on this operators in this work. So here it's μ+1 evolutionary algorithm. You can imagine you have now it's like, for example, your mu is 20 population, and now in which iteration you add only one new offspring we produce. And then you have 21 and you again evaluate and you start again with 20. So you improve only a little bit, but fast, And this is our setting. So we use here Chebyshev inequality, where we here assume then we have accepted value mu of x in our variance. And for Höfling bond, we assume then each element take profit independently of another items with the same dispersion. So we use we calculated this change constraints formulation in our Chebyshev and Höfling objective function. And also we are able to, for first time, to use comparison between the two Chebyshev and Höfling fitness function, actually, which is to use in which scenario it's better. And here we have like several, again, experiments. So we have like different alpha levels, also different mu. I'm on the mu, and thank you. So we have here like uncorrelated and strong correlated data sets with different number of items, and here the main results are here, how you can see it's. So we can improve the simple 1+1 algorithm using different mutation and also using higher population size in this case. So for sure we can improve as the simple 1+1 if I'm only one solution and we compute one solution. And we maximize this profit value, and again in this case, we have the probability of obtaining this profit is less than p is upper bounded to our alpha. in here again, here's the data with Höfling function and different cases and also different alpha. And again, we also show even here it's AI with this different mutation, and here it's new crossover operator are able to outperform AI, the simple AI, but also here this mutation, especially for this kind of complicated higher number of items, got also better results. You can see it's like this algorithm outperformed this fat algorithm. And to do the conclusion is, so I hope I could show you that many rewards problems have like include like the stochastic elements, and they have like different components of this problem, and using the strength constraints allow us to limit this uncertainty with respect to the constraints, but also objective function value. And also we discuss here different approaches, how we use evolutionary computation for these problems. And we incorporated these tiles bonds into the constraints, but also to objective function and in order to deal with this uncertainty. And overall, my message is like at least multi-objective evolutionary algorithm allow us to tackle the problem and give us good theoretical and empirical performance. Thank you.
In practice, suppose we run some algorithm and see the performance, and if it doesn't work, so what do you do in general? Like some hyperparameter needs to be tuned appropriately.
Yes.
Is there a systematic recipe to improve the performance?
Yeah, actually, we built our study like differently. We first look at for the theoretical perspective. So, and this gives us actually, if we run the experiment, give us maybe we have like some expertise in these parameters. So it's actually we don't expect don't expect any failure. Maybe in code would be because we just compute this theoretical. They are not like good and bad parameters, but because it's randomness, so we can see like, okay, we just take simple kind of instances, hard instances, higher number of items. This can evaluate, but somehow we get this trend, yeah. So just which algorithm will work on this higher different problems, and when they outperform, like for example, greedy. So actually, yeah, actually, if we experience some, it's some randomness, but the trend it's kind of straightforward after this theoretical investigation. But for example, it's also interesting because if we also this we look at here, for example, we have Chebyshev of Höfling, and it's like we see it's sometimes one it's performed if we have this less uncertainty, and another we have higher uncertainty. So it's like get us again new insight, and also we just like really compute. Mathematical the point in which the switch, when it's good to take another tile. So, but I think like especially evolutionary algorithm with some hybrid or parameter that are just like there are different in evolutionary computation also branches they look more on automatically parameter performing and so on. But it's not like we are working more on this algorithmical parts.
But still, there are any
Yeah.
tuning parameters? Because almost all machine learning algorithms have tuning parameters, even though we have some theory. Like convergence rate can be guaranteed for any parameter, but the constant may depend on the choice of hyperparameters.
Yes, there are some tools, and we are using some research with we just won't have be more exactly, and you can use compute compute this the best parameters for this kind of problem or setting. Yeah, this is also possible.
Oh.
But how you can see, we just like we show more the landscape, yeah, in the sense how this perform. But we had also some study. I think this is like in AI. It's like function a few years ago. Yeah, you can have like performance and then improve your parameters.
So I'm not quite familiar with the like standard style in Bayesian optimization results. Like, do they also like count the time for hyperparameter tuning?
For the Bayesian inference, I think it's not so serious because it gave the distribution assumption for each hyperparameter as well, so it can be done systematically to optimize not only those variable related distribution, they also optimize the distribution for hyperparameters. So I think it is not so big problem for the Bayesian inference, but yes, I have a similar question maybe with because in the algorithm, there's really lots of tuning parameters, like the percentage of the mutation, number of individuals, or something else. Yeah, but I guess is it because the problem given that it's not so large scale, so maybe it's not so sensitive to the choice of hyperparameters.
Yeah, I think here that there are like how to say like a mutation at all, then will be more crossover application. And yeah, we just we don't make hyperparameters on this. We just more from expertise on this algorithm and this problem. You know, okay, 0.8. Yeah, this is like, but we don't. This will be even better results, yeah, if we have this, but it's like only on this priori knowledge in this sense, and I think it's more the focus on this, and we have some study how I say would we have done this parameter. It's kind of also time consuming, and then we want to see on this one snapshot kind of.
Yeah, I think optimizer is a hyperparameter. Is always very challenging and time consuming for all different algorithms. Yeah.
If there's no more questions, then this is the end of today's seminar. Thank you for your great. Thank you.